Good morning, class. Welcome to the continuation of our Probability and Statistics class, Chapter 4 Estimation of Parameters. For this lesson, we're going to discuss confidence intervals for the population mean when your standard deviation or sigma is unknown. So, the objectives are first, identify the appropriate distribution when the population sigma or your standard deviation is unknown. Second, understand the t distribution. State the difference between a z distribution and a t distribution. And lastly, identify the confidence coefficients for computing t from the t table. Other than sample sizes, it is likewise important to consider the population standard deviation when estimating confidence intervals for the population mean. There is an appropriate distribution when the sample size is small, such that the central limit theorem cannot be applied and the population standard deviation is unknown. So today, we're going to explore this concept in this activity. Adre wants to know if cooperative grouping is an effective strategy in improving the mathematics performance of grade 7 students. 20 students were included in the experimental group, while another 20 students were included in the control group. The mean achievement score of the students in the experimental group was 82.5 with a standard deviation of 3, while the mean of the students in the control group was 80 with a standard deviation of 6. The two groups come from normally distributed populations. The confidence level was adopted 95%. So the first question, what is the estimate population mean when the experimental group comes from? Second, what is the estimate of the population mean where the control group comes from? Lastly, express your confidence as percentage. So, based on this question, you will notice that the population standard deviation for each group is unknown. In statistics, there is a method that we can use to compute confidence interval for population mean when your standard deviation or your sigma is unknown. However, there are assumptions to bear in mind. When n is greater than or equal to 30 and your standard deviation or your sigma is unknown, the sample standard deviation scan can be substituted for your sigma. However, the following assumptions should be met. So first, the sample is a random sample. Second, either n is greater than or equal to 30 or the population is normally distributed when n is less than 30. Okay, so in the past lesson, when your standard deviation is known and the sample size is 30 or more, or the sample size is less than 30, but comes from a population that is approximately normally distributed, the confidence interval per the population mean can be found by using your Z distribution. So very often, however, sigma, or your standard deviation, is not known. So, it must be estimated by S, the sample standard deviation. So, when S is used, especially when the sample size is small, critical values greater than the values of your z sub alpha over 2 are used in confidence intervals in order to keep the intervals at a given level, such as the 95% level. So this means that a multiplier of the standard error of the means is denoted by s over the square root of your sample size n. That is reflected in a wider confidence level. But the number of your standard errors needed for the zero point 0.9 or 0.95 confidence interval depends on the sample size. So with small sample size, more standard errors are needed to span the zero point 0.9 confidence interval. So this number of your standard deviation or your S over the square root of your sample size and values is called the T distribution. The general expression for the confidence interval when your sigma or standard deviation is unknown is given by mean plus minus t multiply by your sample standard deviation over the square root of your sample size n. And the distribution of values is called t distribution. So this concept of the degrees of freedom is used in the t distribution. The degrees of freedom denoted by df are the number of values that are free to vary after a sample statistics has been computed. And they tell us the specific curve to use when a distribution consists of a family of curves. For example, if the mean of 5 values is 10, then 4 of the 5 values are free to vary. But once the 4 values are selected, the fifth value must be specific number to get the sum of 50. Since, thus, if n, your sample size n, is equal to 5 and the degrees of freedom or your df is equal to n minus 1, that is equal to 4. The tea distribution was formulated in 1908 by an Irish brewing employee named William Seeley Gossett. Gossett was involved in researching new methods of manufacturing ale because brewing employees were not allowed to publish results. He published his findings using the pseudonym student. Hence, the T distribution is sometimes called student's T distribution. So the formula for computing the confidence interval using the distribution is here. So your mean minus T multiplied by the sample standard deviation over the square root of your sample size n, which is less than the population mean but greater than your sample mean plus the t distribution multiplied by the sample standard deviation over the square root of your n. The t-values found in the reproduced t-table are the proportions of the area in two tails of the t-curve. They are called critical values of t, in the sense that they are the boundaries of the middle area where the true mean lies. Like the z, they are also called the confidence coefficients. This will be your t-table. So note that in the table, the t-values are based not on sample size n, but on degrees of freedom, which is n minus 1. So for example, n is equal to 20. The zero point 0.5 or 95% confidence interval when your standard deviation is known is mean plus minus 1.96 multiply by your standard deviation over the square root of n. But when your standard deviation or your sigma is unknown and only s is available, the zero point 0.5 confidence interval is sample mean plus minus 2.09 multiply by your s over square root of n. So, the confidence coefficient is 2.09. Okay? Likewise, in the t-table, for n is equal to 10. Okay? The 0.095 or 95% confidence interval is Sample mean plus minus 2.26. Okay, so here, multiply by your sample standard deviation over the sample size of your n. So the confidence coefficient is 2.6. So which is here. Here. Since the population standard deviation and the standard deviation of the sampling distribution of means are rarely known, the procedure involving T is typically used in setting confidence interval. So we have the following four-step method that will be helpful in determining the interval estimate for the population mean when your standard deviation or your sigma is unknown. So first, we're going to describe the population parameter of interest. Second, specify the confidence interval criteria. So here we're going to check the assumptions, determine the test statistics to be used. In this case, it is the T statistics. So third, state the level of your confidence. We're going to collect and present sample evidence, collect the sample information, and then find the point estimate. Last procedure is to determine the confidence interval. So first, we're going to determine the confidence coefficient, that is T sub alpha over 2 from your T table. We're going to find the sample standard deviation over the square root of your sample size n. Then we're going to find the lower and upper boundary or confidence limits. Lastly, we're going to describe the results. So let's have an example to understand this better. An admission officer of an educational institution wants to know the mean of age of all entering mathematicians major. He computed a mean age of 18 years and a standard deviation of 1.2 years on a random sample of 25 entering mathematics major, purportedly coming from a normally distributed population. With 99% confidence, find the point estimate and the interval estimate of the population. Let's look at our first example. So for this, we're going to use the four-step method to find the estimates of the population means where the experimental group and the control group belong as a given in our activity. For our first step, we're going to find the point estimate. So we're going to describe the population parameter of the interest. So for the first parameter of the interest is the mean. So we're going to label it as this one. So this is the mean of the population where the experimental group belongs. Okay? Experimental group. For our second parameter of interest, which is the mu sub 2, the population were the control group. Okay, control group. Okay, so for our next step, we're going to specify the confidence interval criteria. First, we're going to check the assumptions. So the sample size of 20 for each group come from a normally distributed parent population, and the standard deviation for each group is unknown. Okay, so let's put it here. Next is we're going to determine the test statistics to be used to calculate the interval. So the test statistics is T. Using your L sub 1, the standard deviation for your experimental group is 3, and the sample standard deviation for your control group is 6. Now we're going to state the level of our confidence. So for this, we're going to use the 95% confidence. Okay? So it has an alpha that is equal to 1 minus 0.95. That will be equal to 0.05. And from the T table with a degree of freedom that is 19, so let's put it here, equals to 19. For each group, the confidence coefficients are positive, negative 2.10. Okay? So now we're going to collect and present sample evidence. So for the first step, we're going to collect the sample if information. So the sample information consists of 20 rows. Remember, for each row, for 20 row scores for each group. So from the experimental group, okay, let's put it here. This is your experimental group. So we have N is equal to 20. And then your degree of freedom is 19. Your mean is 82.5. And your sample standard deviation is 3. Okay, so now for your control group, we have N is equal to 20. The degree of freedom is equal to 19. Your sample mean is 80 and your sample standard deviation is 6. Lastly, we're going to find the point estimate. So the point estimate for the population means are the sample means. So therefore, the point estimate for your experimental group is 82.5 and the point estimate for your control group is 80. Next, we're going now to find the 95% confidence interval. To find the 95% confidence interval, we need to determine the confidence coefficients. Since our n is 20 and our degree of freedom is 19, the confidence coefficient in the t-table under 0.95 or 95% is 2.10. Now, the next process is we're going to find the maximum error E. So, for the experimental group, so we have T sub alpha over 2 multiply by your sample standard deviation over the square root of your sample size n. So, that would be 2.10 multiply by 3 over the square root of 20. Okay, so 2.10 multiplied by 0.67, it will give us an answer of 1.40. So this is the maximum error for your experimental group. Now, for the control group, so same formula, that will be 2.10 multiply by 6. Now it will be 6 over square root of 20. So 2.10 multiply by 1.32. So it will give you an answer of 2.81. So this will be the maximum error for your control group. Now, the next step, we're going to find the lower and upper confidence limit. We're going to use this formula. So, sample mean minus your t multiplied by sample standard deviation over square root of your sample size n less than the mean but greater than, so that will be positive t s over square root of n. Okay, so for the experimental group, so we have um, 82.5 minus what is our maximum standard, maximum margin error, that is 1.40. So it will give us an answer of 81.1. So this is your lower limits. For the upper limit, it will be 82.5 plus 1.40. So it will be 83.9. So this is for your upper limit. Now, for your control group, we have 80 minus 2.80. So that will be 77.2. This will be the lower limit for your control group. Next, 80 plus 2.80. So this will be the upper limit for your control group. So for the results, we can say that with 95% confidence that the interval between 81, so 81.1 and 83.9 contains the true mean of the experimental population. So this is for your experimental population. And for the interval between 77.2 and 82.8 contains the true mean of the control population based on the given sample data. So this is how you solve or compute population mean when your standard deviation is unknown. We're now on our lesson 4, which is point estimate for the population proportion P. And our objectives are: first, understand the population proportion P, illustrate the sampling distribution of the estimator of P, state the characteristics of the sampling distribution of the estimator of P. Fourth, identify the point estimator for the population proportion P. And lastly, compute the point estimator of a population proportion P. So, surveys are common to elicit people's perception about emerging issues. So, they provide information to the public so that they may be guided accordingly into their day-to-day action. So, for example, in Everyday, a TV network conducts a public opinion survey on issues that relate to our president's policies, people's health, government officials' conduct, and so on. Barangays conduct surveys to determine the number of constituents in their respective areas. Many decisions are based on countable observations obtained from surveys. However, to be credible and meaningful, these countable observations should represent a random sample from a target population. For example, TV networks should report service results obtained from randomly selected correspondents on a target population. So let's explore this one. On a typical morning, Anthony asks his TV viewers if they believe or do not believe the great escape story of a group of soldiers from a perceived adversary. At the end of his show, he reported that 68% of the correspondents believed the story. So we're going to question, what does the report mean to us? What do we understand by the expression 68%? The percentage expression 68% is also called your proportion. Percentage are preferred when reporting frequencies of subsets of population, but in computing, percentages are first converted to proportion in decimal form. Proportions also represent probability. So, the probability that all TV viewers favor the Great Escape story is 0.68. Proportion can also be obtained from samples or population. So, we're going to use the following symbol: N, which is equal to the number of observations in a simple random sample, your P hat, or the sample proportion, P, population proportion, P hat is equal to the number of desired outcomes over the numbers of your sample element. For a sample proportion, P hat is equal to your X over N, and Q hat is equal to 1 minus P, where X is the number of sample elements that possess the desired characteristics and N is the sample size. For example number 1, a random selection of school children were asked whether they like, do not like, or cannot decide whether they like or not a new kind of snack served by the school cafeteria. So their responses are shown as follows. So here, first question, what is the proportion of correspondents who like the new snack? B. What is the proportion of correspondents who do not like the new snack? Third, what is the proportion of correspondents who cannot decide? Number 1, so there are 31 who like the new snack. So we're going to label it as P of hat or P hat sub like is equal to 31 over 60. So our proportion would be 0.516 or 0.52. Convert this into percentage, that is 52%. Now, for the responses that do not like, so there are 14. So P hat do not like, that will be 14 over 60, which is equal to 0.23 or 23%. And lastly, there are 15 that cannot decide. So that will be P hat can't decide is equal to 15 over 60, and that would be equal to 0.25 or 25%. For example number 2, in an island, 72% of the population can swim. So, meaning that will be 72 out of 100 that can swim. As a fraction, this is expressed as 72 over 100, where 72 is the favorable responses that can swim. So the decimal value of that is 0.72. Third example, in a job satisfaction survey in a certain mall, 700 employees were asked if they were satisfied with their jobs. There were 518 who responded with a yes. What proportion is this? What proportion responded with no? For this question, we need to determine what is asked. So first, what is the proportion responded with a yes? And second, what is the proportion responded with a no? So next step, we're going to specify the given information. Your X would be 518 and your N would be 700. Then we're going to represent the desired proportion. Let's represent P hat as your proportion of yes responses. Okay? Yes responses. Now, let's use Q to represent the proportion of no responses. Then we're going to write the formula for P hat. That will be X over N. And for the Q hat, okay, put it hat. That will be 1 minus your P hat. So next, we're going to substitute the given values in the computing formula. For the P hat, so solution, this will be our second step, our third step, and our fourth step. Remember, our first step, that is to determine what is asked. Okay? So for your solution, that will be P hat is equal to 518 over 700, which is equal to 0.74. Now, for your no responses, that is Q hat, that will be 1 minus 0.74, which is equal to 0.75. 26. So your conclusion or the answer, the question that is raised in the problem, the proportion of yes responses is 0.74. So this means 74% of the responded yes, and the proportion of no response is 0.26. That is 26% for the no respondent. So 74% for the yes responses and 26% for the no responses. So if you add these two, it will give us an answer of 100%. In our example, you will notice that proportion is a fraction expression where the favorable responses is in the numerator and the total number of respondents is in the denominator. The basic operation involves division. Thus, the result is a decimal value that can be expressed as a percent. So there are characteristics of the sampling distribution of p hat. So first, the mean of the sampling distribution of p hat is p. That is, p hat is the unbiased estimator of your p. Second, the standard deviation of the sampling distribution of p hat is square root of p times q over n. That is sigma multiplied by your p equal to the square root of your p times q over n, where q is equal to 1 minus p. Lastly, for large samples, the sampling distribution of your p hat is approximately normal. A sample size is considered large if the interval p hat plus plus minus 3 by your sigma times p does not include 0, like p is equal to 0.001 or 1, like p is equal to 0.009. So let's go back in the job satisfaction survey in our example. So the point estimate for the population proportion is 74%, if you remember. So this means that if we were to draw random samples of 700 people over and over again, each time calculating a p hat, like the sampling distribution of the mean proportion would be 70. Let's have example number 4. In a survey of 300 individuals, 128 like to watch movies on the big screen. Estimate the true population proportion P and Q, where P hat is the proportion of those who like to watch movies on the big screen based on the sample. So since X is equal to 128 and your N is equal to 300, your P hat would be X over N. So substitute this, we have 128 over 300, which will give us an answer of 0.426. Round this off to two decimal places, that is 0.43. So the estimator of P is P hat, and the estimator of Q is Q hat. So thus, the population proportion P is 0.43. And since Q is equal to 1 minus your p hat, then that will be 1 minus 0.43. So the answer would be 0.57. So therefore, there will be 43% who likes to watch movies on the big screen, and then there will be 57% who do not like to watch movies on the big screen.